Particles, fields, and the future of physics. Particles, you know what that is. You know what the future of physics is. Secretly, my hidden agenda that you can't get away from because you're here now is to do quantum field theory. That's what I really want to teach you tonight. So I'm very glad that Fermilab is giving me these 6 hours to really give you enough of a taste of what quantum field theory is really all about. So I was lucky enough last July of 2012 to be spending my Independence Day in Geneva, Switzerland, at CERN, where it was a rock concert-like atmosphere. There was this event, it was planned, the announcement went out, people lined up, people camped out overnight, literally. It looks like the people camping out before a rock concert, except there are a lot more Macintosh laptops in the audience than otherwise. And there was no rock concert the next day. There were 2 PowerPoint presentations. What in the world would be the content of a PowerPoint presentation that would be good enough that would make people camp out overnight? Well, of course, this was the announcement of the discovery of what we now know is the Higgs boson, a particle that physicists have been looking for literally decades. And we were finally able, through thousands of people working together, billions of dollars spent, decades of effort, to find the evidence for this particle called the Higgs boson. So there are 2 questions that you should be asking about this event. One is, what is the big deal? Of all of the events maybe in humankind, it's hard to think of one that has a greater ratio of excitement generated in the general public divided by people knowing what's going on. It's very difficult to explain why this is people get it. You know, they appreciate, they see the physicists walking around buzzing with excitement, but they don't actually understand what the excitement is about. Maybe you don't until tonight. And the next question, of course, is what's next? You know, that's good. You've done something you've been trying to do for decades, so we're all about, you know, what is happening in the next 30 minutes or 2 minutes in the Twitter age. So tell me what we're going to do next, and that's what I want to talk about a little bit today. So the story that we're tracing goes back to this guy, Democritus. Democritus, an ancient Greek, he lived 2,500 years ago, and he's arguably the first theoretical particle physicist. He was not an experimental particle physicist. They didn't have those back in ancient Greece, but Democritus and his friends, Epicurus, Lucretius later in ancient Rome, these were the early classical atomists. These were the people who were saying that we look around us, we see this incredible variety of stuff. There are living beings, there's the air, the water, the earth, there's materials around us. And these guys said, you know what, they're not all fundamentally different kinds of things. They're the same fundamental ingredients arranged in different ways. It's the atoms of different materials, the fundamental particles that get put together in different ways to make all the wonderful variety we see around us. Now, the word atoms, which is what they used, was sadly stolen by the chemists in the 19th century to denote the chemical elements. But what they really were talking about were what we would call elementary particles, the particles of which there's no smaller little pieces. This is not a photograph of Democritus. There are no photographs or even sketches of what Democritus looks like. But in addition to being a famous atomist, he also had a great nickname. Democritus was known as the laughing philosopher. So when the Renaissance came along and it became possible to earn a living painting things, and classical subjects were very popular, people would paint self-portraits and call them Democritus because they wanted to paint a self-portrait of themselves laughing. So this is Rembrandt, the young Rembrandt. He labeled it Democritus, doubles the price at the auction for your painting. Now, 2,500 years later, where do we find ourselves? The particle physics, as we currently understand it, is truly something that really got going in the 20th century. There were, little things going on in the 19th century as well, but by the 1930s, we had put together a pretty good picture of what matter and forces are. You could have forgiven a 1935-era physicist from thinking that, we were pretty close to getting it all right. We had this idea that they were atoms, and people like Rutherford and Bohr had put together pictures of how the atoms worked. The atom was not, there were old ideas of plum pudding and so forth, but the new idea is that there is a small, dense nucleus at the center of the atom, and there are electrons, lighter particles, electrically charged, orbiting around the nucleus. And since then, people learned that the nucleus was a combination of positively charged particles called protons, neutral particles called neutrons. What kind of chemical element you have just depends on how many protons you have. So you have three particles, protons, neutrons, electrons, and there were three forces that were pushing them around. There's the electromagnetic force. Back in the 19th century, we'd unified electricity and magnetism. The electromagnetic force takes the negatively charged electron and pulls it toward the positively charged proton. There is some nuclear force. No one knew anything about that in 1935, but they knew that something was making the protons and neutrons stick together. So there's some nuclear force that holds them together. And then there's gravity. Gravity pulls everything to everything else. It's absolutely universal. It's shameless gravity. It does the same thing to everybody. And the remarkable thing is that in the course of scientific progress, we learn more things. Sometimes that learning causes us to throw out previous knowledge. Sometimes we just absorb and expand on it. This picture that we put together in 1935 remains true to this day, and it will remain true forever. It will always be true that people like you and me are made of atoms that are made of electrons, protons, and neutrons. We've added to the picture, such so that by the 1980s, here is the kind of picture we had. So we knew that there are still protons and neutrons, but we know they're not elementary particles. Protons and neutrons, the nucleons, the stuff that make up the nucleus, are actually made of smaller particles called quarks. We had the up quark, the down quark, and there's two ups and a down in a proton, two downs and an up in a neutron. So it's a very simple picture of how to put together protons and neutrons. Then we needed one more particle because the nuclear force got split in two. And because particle physicists are brilliant at naming things, they called it the strong nuclear force and the weak nuclear force. There's a little footnote saying that was sarcastic when I said that particle physicists are brilliant at naming things. The strong nuclear force is what holds the quark together, the quarks inside the nucleons, and then there's like extra leakage of the strong force is what actually holds the neutrons and protons themselves together. But there's something else that goes on. Inside the sun, for example, when two protons smack together, they fuse, but what that means is that one of those protons turns into a neutron. Where does the extra electric charge go? It spits out an electron, or an anti-electron, and then another particle called the neutrino. This is not run by the strong nuclear force. There's a whole new force called the weak nuclear force, and it needs the neutrino to make it work. But otherwise, the picture is the same. So instead of three particles and three forces, we have four particles and four forces. Over 50 years of effort, and we made one more particle and one more force. But sadly, it's a little more complicated than that. The rule to thinking about, if you want to guess about the future of physics, just guess what is it that will make the lives of physics graduate students the most difficult. So we took this picture, it works very well, and then we duplicated it 3 times. So there's not only an up quark, a down quark, an electron, and a neutrino. That family of particles, or that generation within a family, there's another generation of heavier particles and another generation heavier than that. The first one of these we found, the electron, its heavier cousin is called the muon. And literally, the famous physicist I. Rabi, when the muon was discovered, he said, "Who ordered that?" The muon does nothing useful to us. It just is a heavier cousin of the electron, and there's another heavier one called the tau. And the up and the down quarks, they have heavier cousins called charm and strange, and yet heavier ones called top and bottom. We still don't know why there are 3 generations of elementary particles. But the picture remains more or less intact. So if we add those little bells and whistles, we have a theory. We have a model that you can put on a T-shirt. It would be a complicated T-shirt. Here's the T-shirt. So this flow chart answers the question, if you know you're an elementary particle but you don't know which one are you? So despite the fact that there's this whole zoo of particles, there's an organization. There's a pattern to what is going on. So you ask yourself a series of questions. The first thing you ask is, if you put 2 particles on top of each other, do they like being on top of each other, or do they take up space? Is it hard to put 2 particles right at the same place? If it's easy to pile on, then you're a boson. If it's hard, if you take up space, you're a fermion. Fermi, named after Fermilab. No, it was not named after Fermilab. It was named after Enrico Fermi, who got the particles and the lab named after him. So fermions are the particles of matter. They take up space. Atoms, the electrons, the quarks, the protons, and neutrons are all fermions. So the question of if you're a fermion is, do you interact with a strong force or not? If you do, you're a quark. If you don't, you're a lepton. That's where the electron and the neutrinos are, as well as their heavier cousins. If you pile on top, then you can give rise to a force. The force-carrying particles are the bosons. And so you get the weak interaction bosons, the gravity boson is the graviton, the strong force boson is the gluon, the electromagnetic boson is the photon. And then way up here in the corner in a different color, there's another kind of boson that does not give rise to any noticeable force, and that's called the Higgs boson. So the Higgs boson is the last of these particles to be discovered, and it's also the weirdest. It's the one that doesn't fit. It's the one that doesn't make sense. You have matter particles, and you have force particles, and then you have the little Higgs boson up there. Why did we need to invent the Higgs boson? The idea of the Higgs was invented in the 1960s, the early 1960s, long before it had been discovered. So clearly there was some need to invent it. And if you want to know why the discovery of the Higgs was so important, you need to know why we invented it in the first place. And that's what's difficult to explain. And the reason why it's difficult to explain, you can blame Democritus, because he's the one who got us started thinking about particles. And if you have a little bit of physics education, you might have faced this point where your teacher, your professor is telling you, is light or is matter or electrons particles or waves? This is some sort of dichotomy you want to resolve. And I'll bet you, 10 to 1 odds, they didn't tell you the answer. The answer is it's waves. You need to understand what is going on. You actually need to give up a little bit on the notion of particles. So rather than pointing at Fermi or Democritus, my touchstone in the intellectual tradition for dealing with the real world is the Insane Clown Posse. This is a young group of, these are two singer-songwriters in the hip-hop tradition. This is Violent J, and that's Shaggy 2 Dope. These are not the names they were born with, but and you know they tend to have themes in their musical stylings, mostly in dealing with partying and having a good time. But a couple years ago, the Insane Clown Posse came out with a song that was controversial because it was not about partying and having a good time. That controversy had died. That was boring. They wrote a song called Miracles that was about how awesome the world around us is and how mysterious it is. And in the course of the lyrics for Miracles, the Insane Clown Posse really managed to get scientists annoyed at them. They said the following: I see miracles all around me, stop and look, it's all astounding. Water, air, fire, and dirt, gosh darn magnets, how do they work? That's not the actual word. You can Google the word that they said. And they went on and saying, you know, gosh darn scientists, you don't know anything. So the scientists were, you know, they thought about this because their playlists naturally came up with the Insane Clown Posse. And they were puzzled because they were like, you know, guys, magnets, it's part of our wheelhouse there, magnets. We kind of do understand how magnets work. So what I want to do, it's true, we do actually understand magnets. There are things we don't understand. Magnets, not the first thing to choose. But I want to nevertheless give some points to our plucky duo, because even though we understand how magnets work, it is still true that they are astounding. And we sometimes forget that because we understand how things work. We forget how strange it is, the way that different things work. If you think about a magnet, what does a magnet do? A magnet sticks to your refrigerator. But lots of things stick to your refrigerator, right? A piece of tape would stick to your refrigerator. A gecko would stick to your refrigerator. That's not surprising. What's surprising is that the piece of tape, in order to get it to stick to your refrigerator, has to touch the refrigerator. That makes sense. It has to sort of cling. There has to be some part of the piece of tape that is interacting with the refrigerator to keep it stuck. But the magnet, if you hold a magnet close to the refrigerator, you know it starts pulling on the refrigerator. It starts pulling toward there before it actually touches. How does the magnet know that there's a refrigerator nearby that it needs to stick to? How does the magnet reach across space and say, yes, refrigerator, good, I'm ready for this. I got this. How do they work? That is a very respectable question. It's not only Violent J and Shaggy 2 Dope who want to know, it's this guy, Isaac Newton. Isaac Newton, very famous for inventing gravity. He didn't invent gravity, it's been around for a long time, but he invented the law of gravity that really works. And it's not the perfect law because Einstein came up with an even better one. But Newton's version of gravity is good enough to get you to the moon, for example. And it was a very simple idea. His idea was that gravity was universal and that it obeys a certain very simple mathematical relationship. Here's the Earth. Here's some objects, some satellites that NASA has built flying around the Earth. And Newton says there's a gravitational pull on every object that is proportional to the mass of the object pulling it, which makes sense. But also, it gets fainter and fainter the further you go away as the distance squared. It's the inverse square law. The bigger the distance, the weaker the force. And that simple idea, the force of gravity goes as 1 over the distance squared, works for apples falling from trees, works for the moon going around the Earth, it works for stars going around the Milky Way. It's incredibly effective. The problem was, from the 17th century point of view, when Newton was thinking of this, it made no sense. Newtonian gravity in Newton's day was a lot like quantum mechanics is to us today. It's a theory that fits the data beautifully. It's obviously right, but there's a part of it that doesn't really make intuitive sense to us. For Newton, it was this aspect of action at a distance. So you're over here, you're this guy, you want to know what is the gravitational field pulling me right or left or whatever. What is the force on me due to gravity? And Newton says all you have to do to figure out the force due to gravity is take every object in the entire universe, figure out how far away it is, how much mass it is, and apply the inverse square law. And people said, that seems strange that I need to understand every object in the universe to figure out what the gravitational force is on me right here. Why? That seems spooky. It's action at a distance. It's like something going on in the Andromeda Galaxy is affecting me right here, right now. And Newton was very, very bugged by this. He says, this makes no sense. I leave the mechanism for how gravity actually functions to smarter people in future generations. He knew that it was a puzzle. So the puzzle actually was resolved, and this guy does not get nearly enough credit, by Pierre-Simon Laplace in the 18th century. He was a famous physicist and mathematician. And he's famous for telling Napoleon that he didn't need to use God to explain the positions of the planets, which might seem cheeky and very out of character for Laplace because he was basically a social climber, but his wit got ahead of him that one time. Anyway, long before Napoleon, Laplace was puzzling about this idea of gravity. He was trying to understand the shape of the Earth, the motion of the planets. And what he realized is you could take Newton's theory of gravity, the inverse square law. He didn't change the theory. He said you could rewrite the theory by imagining that there is a field filling space. So what is a field? A field is just something that fills space, that takes on a value everywhere. So the temperature of the air in this room is a field. At every point in space, there's a temperature value. But temperature is obviously not fundamental. It's a property of the air. The gravitational field that Laplace is talking about, this is a thing, this is a fundamental ingredient to reality. And Laplace came up with an equation that his gravitational potential field obeyed. And he says that through this equation, he could exactly reproduce all the predictions of Newtonian gravity. So now, here is the Laplacian picture of how gravity works. Here's the Earth. Here's the gravitational potential field, has a value at every point in space. It's low here, it's higher here. And Laplace says that the force that you feel due to gravity is just the slope of this field. If it's tilting down a lot, gravity is strong. If it's tilting just a little bit, gravity is very, very weak. Exactly the same experimental predictions as Newton. Why is this better in some sense than Newton? Because to figure out the force due to gravity here, I don't need to know the universe infinitely far away. If someone told me what was going on in a sphere around that particle, if someone told me the gravitational potential in some region, that would be enough. Once you invent field theory, the laws of physics are not action at a distance, they are local. The information you need is contained nearby you. The mechanism for why gravity works is now explained. It's not instantaneous weird communication over infinite distances. It's that the Earth pushes down the field right there, and that pulls the field right there, and that pulls the field right there, and that pulls the field throughout the rest of space. Everything touches everything else and communicates to its nearest neighbors, not to the whole rest of the universe. So that paradigm seemed to be extremely effective. By the 19th century, we had a picture of physics where matter, stuff, was made of particles, atoms. Atoms became sort of accepted by the modern scientific community in the 19th century. And forces, we said, are made of fields. The electromagnetic field was understood in the 19th century, as well as the gravitational field. The 20th century was more absolutist in its leanings. The 20th century comes along and says, you know what? That particle stuff is overrated. Actually, everything is made of fields. You don't need to separately talk about matter made of particles and forces made of fields. All you need are fields. That should puzzle you a little bit. How can it be? I'm telling you, and I'm not going to back off this later, this podium right in front of me is made of fields. Little vibrating numbers at every point in space are what make up this podium, are what make up me and what make up you. But we feel solid, right? How can it possibly be that something as tangible and solid as ourselves or the Earth can be made of vibrations or oscillations or gradients in fields filling space? Well, the answer, of course, is quantum mechanics. Quantum mechanics is what you need, and when you add quantum mechanics to fields, you make quantum field theory. This unhelpful little graphic is just to point out an interesting fact, which is that to working physicists, quantum field theory is the most important thing we know. We learn quantum field theory in graduate school. There are billions of books written about it, from quantum field theory for mathematicians to quantum field theory for dummies. And how is quantum field theory possible? I didn't read that book, but it is possible. It works. The point is that when we talk about physics to non-physicists, when we popularize it, we never mention quantum field theory. We talk about particle physics, we talk about relativity, we talk about quantum mechanics. Heck, we talk about string theory in the multiverse and the anthropic principle, but we think that quantum field theory, it's too much to bother about. And as a result, no one got it when we discovered the Higgs boson. Because to understand why the Higgs boson is important, you need quantum field theory. So let me remind you, in case your quantum mechanics has become a little rusty, what quantum mechanics is all about. The motto of quantum mechanics is that what we see when we look at the universe, what we can observe or measure, is in principle very different from what actually exists out there in the universe. In classical physics, in Newtonian physics, there was a particle or a field, that's okay. The particle has a position, it has a velocity, the field has a value, and it has a change in time. And if you tried hard enough and worked carefully enough, you could measure any one of those values with as good precision as you could possibly want to get. Quantum mechanics says that reality is fundamentally different than that. That there's something going on that you can never see directly. That what you see when you look at the universe is different than what the universe really is. And that bugged people when it was invented, and it continues to bug people today. So for example, a spinning top, it turns out that in quantum mechanics, the allowed values that you can measure of the spin of the top are fixed. There's a fixed set of possible answers you can get when you ask how fast is the top spinning. Now the minimum possible answer turns out to be a quite small amount of spin. So you're not going to do this experiment. Even Fermilab is never going to do this experiment. If you took this top and said, can we rotate it the slowest it is possible to rotate a top, it would turn around once on its axis once every 100 million times the age of the universe. So it's very slow. But if you have an elementary particle, then this discreteness of observable amounts of spin becomes very, very important. That's why quantum mechanics first came into our notice when we started studying elementary particles. So this feature that certain observable features are quantized is where the word quantum mechanics comes from. And so quantum mechanics says this idea that there's an electron, a particle, and it has a position and it has a velocity is just wrong. It's not that we can't measure the position and the velocity, it's that there is no such thing as the position and the velocity. What there is a wave function. There is a wave spread throughout space that answers the question, what is the probability that we will measure the position of the electron if that's what we choose to measure. So this is an actual mathematical model of a certain wave function for an electron in an excited state. And this is saying that you're not going to see the electron out here, but you might see it up there, you're not going to see it there, et cetera, et cetera. The wave function is what really exists. It's what the field, the equations of physics govern their evolution through time. But when you look at the electron, you don't see the wave function. You see the electron in a position. And that should bother you, and we're still trying to do better. But that's how reality works. So this is quantum mechanics. Glad we got that straightened out. You add quantum mechanics to fields, and you get quantum field theory. So fields mean that the fundamental ingredients of reality are not particles. They're things that take on values everywhere throughout space. But quantum mechanics says when you look at the fields, you don't necessarily see this nice, smooth, undulating fieldness of them. If the fields are only vibrating a little bit, when you look at them, they resolve into individual packets of energy, and it is those packets of energy that we call particles. So particles are just small vibrations in quantum fields. And part of this is actually familiar to you. The light that is coming to us from light bulbs, we know that we can talk about that as a wave, an electromagnetic wave traveling through space. We talk about the frequency of different electromagnetic waves and the wavelength. But we also know that if we look at it closely enough, that light resolves into individual particles called photons. If a friend of yours, if you're camping, it's late at night, it's dark, you have a friend who's carrying a lantern. Something goes terribly wrong and your friend doesn't like you anymore, so they start walking away. You see the lantern get dimmer and dimmer until eventually you don't see it anymore. That's because our eyes are not the best photodetectors we could get. Frogs, it turns out, have better eyes, more sensitive detectors in their retinas than humans do. A frog that sees that lantern walk away would not just see it get fainter and fainter. It would get fainter and fainter until it starts flickering on and off. And as the lantern gets further and further away, it's just off for longer and longer periods, and the flickers become further and further spaced apart. What the frog is seeing is individual photons hitting its eyeball. What is really happening is an electromagnetic wave is hitting the eyeballs of the frog, but the observation turns that wave into individual packets of energy called particles. And I should say, I use the word observation, so people worry that there's something to do with like consciousness or intelligence, or you're changing reality by observing it. It doesn't need to be a conscious being. It could be a frog. It could be a video camera. It could be just any macroscopic collection of many, many different vibrating fields interacting with a single vibrating field resolves it into these individual packet-like quanta of energy that we call particles. And this explains a lot, actually. This fieldness underlying the particles we observe explains things like, how can one particle change into another one? This was a real puzzle back in the early days when they discovered radioactivity. These days we know radioactivity, but in the early days they were like this nucleus of an atom is spitting out particles. It's changing into different particles. A neutron, all by itself in empty space, decays into a proton and an electron, and now we know a neutrino as well. And people were wondering, like, was the electron hiding in there? What is going on? It's very hard, if the world were really made of particles, to explain how they can change into each other. If it's fields, suddenly it makes perfect sense to us. The W boson is a field that is vibrating, that we observe as a particle, but it's unstable because it has a mass. What do you mean by the mass of a field? Masses are things that are connected with particles. The mass of a particle is just the energy it requires to push the field around, the energy that is required to get the field to vibrate. It's like some pieces of string are easy to shake. Some heavy chains require more effort. A heavy chain is like a massive particle. A light little piece of string is like a low-mass particle. And what happens is that the empty space before your eyes right now is full of many different kinds of elementary fields that make up the universe. Not just the electromagnetic field, the gravitational field, etc. For every particle that we mentioned in the flowchart, there is a field. There's a W boson field, there's an electron field, there's an up quark field, there's a muon neutrino field, and so forth. And these fields talk to each other. They interact. They're rubbing shoulders next to each other, and one vibrating field can affect the other ones. It can give its vibrations away to the other fields around it. So you have the W boson vibrating. It can transfer its energy into vibrations in the electron field and the antineutrino field. So now it makes perfect sense that particles change into each other, create each other, destroy each other, annihilate. It's just fields vibrating in different ways, transferring their energy from one field to another. So that was the quantum field theory lecture. I hope all that's perfectly clear. The homework assignments will be handed out at the end of the lecture. Why did I bother telling you about quantum field theory even though nobody does? Because quantum field theory is important for two things. Why the Higgs boson was such a big deal, and what we can do next now that we've discovered that Higgs boson. So when people talk about the Higgs boson, they talk about mass, right? You've heard this. You can't avoid this. They start talking about how the Higgs boson is what gives particles mass. And I struggled because, I was writing a book about the Higgs boson that I mentioned. I've written a book about the Higgs boson. And right now on your iPhone, you don't need to wait. You could buy that in Amazon right now. And it's difficult to explain why you need a Higgs field to give mass to particles. So I thought about why the Higgs field was invented. Well, what were they thinking? And I realized they weren't thinking about giving mass to particles at all. They were thinking about how forces work in nature. And the way that forces work, remember Newton told us about gravity, an inverse square law. The gravitational field fades away as you get further and further away. Why is that? There's a simple geometric reasoning. It's because the lines of force get diluted as you go further away. It's just like that lantern moving away from you. Its brightness also obeys an inverse square law. It gets dimmer because there are fewer lines of light rays hitting your eyeballs. Not only does gravity work this way, but electromagnetism also works this way. However, the weak force and the strong force, the nuclear forces, very dramatically do not work this way. They do not stretch over the long distances that gravity and electromagnetism do. They only stretch over very short distances. The problem that was bugging the people in the 1960s when they invented the Higgs field is, why are the nuclear forces so short range? This is not an accident. This is just math. How is the math avoided? Remember, again, nature will always choose the ways that makes graduate students in physics the most annoyed. So it turns out that the answer, why is the force short range, is utterly different for the strong nuclear force and the weak nuclear force. For the strong nuclear force, it's something called confinement. The lines of force don't just stretch out to infinity. They interact with each other. The strong nuclear force, fittingly, is strong. So what happens is that all the lines of force get bundled together, and it's like they're trapped. It's like someone put a shutter around that lantern, and if your head is inside the shutter, it looks very bright. And if it's outside, you don't see the lantern at all. If your head was inside a proton, the strong force would seem very strong. If it's outside, you don't notice a strong force at all. That's confinement. Various Nobel Prizes were given away for that. The weak nuclear force is not confined. It is absorbed. What if that lantern walking away from you at night was on a foggy night? Then as soon as it gets a little distance away, you suddenly don't see it at all. The light coming from the lantern is absorbed by the fog. The brilliant idea from the early 1960s was the following. Maybe there's a field that we haven't thought of yet that fills all of space and absorbs the lines of force from the weak nuclear force. And that's why it's short range. The lines of force just don't get very far until they are absorbed by this foggy field that pervades all of space. So just to say the same thing in different words, this thing that we now call the Higgs field, it was invented by like 7 or 8 different people, but Higgs has the coolest sounding last name, so his name gets attached to it. All of the other fields that we know about in nature, if you plot the value of the field, remember that's what a field is. It's something that takes on a value everywhere. Well, it hovers around 0 in empty space. If there's a particle there, it'll be vibrating, but most of the time the fields are just sitting there at 0, whether it's an electromagnetic field, the gluon field, the quarks, or whatever. The Higgs field is way up here. Its value in empty space is not 0. So you see the drama of what is being suggested. These guys were saying, no, it's not the weak interactions that are puzzling, it's that you don't understand empty space. It has a field in it that has tangible effects that we can go out and measure. For example, if you poke at it, if you poke this field, you make a particle. We'll call it the Higgs boson. And that's what we've been looking for the 40-some years since the idea was put forward. It was as a bonus, it was in 1967 that Steven Weinberg pointed out that if you take this idea, that they were actually thinking mostly of the strong nuclear force, but if you apply it to the weak nuclear force, Weinberg said, you get a bonus, which is you can explain how particles get mass. This was a little puzzle that most people weren't even really taking very seriously, but in the theories of the day, you couldn't explain why particles like the electrons and the quarks had mass at all. That's because, I'm not going to tell you why that's because. It's a whole thing, and you don't want to go there. But given the fact that the world looks different in a mirror, the fact that parity, the symmetry that you'd like to see in the world between things that we see in front of us and things as they would be observed in a mirror world, in particular the weak interactions treat reality one way and mirror reality a different way, is a simple argument that says that that means that every single particle that the weak interaction interacts with moves at the speed of light, has to have zero mass. Einstein told us a long time ago, if a particle is massless, it zips along at the speed of light. You can never slow it down. That would be bad if that were true. If the electron were massless, remember, electrons are important. They form atoms, right? They're the things that go around the nucleus. So if you want to have two atoms come together to make chemistry, it's the electrons that are doing the work. If the electron were massless, it would not ever stick to a nucleus. If the electron were massless, there would be no such thing as atoms. There would be no such thing as molecules or chemistry or life. The world with massless electrons would be a very, very boring place indeed. There would be no Fermilab, no public lectures, nothing like that. So Weinberg says, if you fill space with this Higgs field, I can cook up a model where the electron interacts. The electron feels the influence of the Higgs field all around it, and that gives it some heft. It makes it harder to push the electron and get it moving. It gives it some mass. It turns out to be spectacularly confirmed. This is a model that made many, many predictions that all come true to very high precision. So the Higgs boson is what makes life itself possible. That is why discovering it was a big deal. Now, if you want to know about new physics we haven't yet discovered, including, let's say I was giving this talk a year ago, we haven't discovered the Higgs boson yet. How do you look for new physics? How do you look for physics you don't yet know? It turns out that quantum field theory tells you how to look for things you haven't found yet. This is like an amazingly wonderful fact, because in classical mechanics, you can just imagine all sorts of different ways that weird phenomena could hide from you. But this idea that the world is made of fields and the fields vibrate and they all talk to each other, that tells you how to look for new fields. You shake the fields that you know hard enough, they will start the other fields vibrating. And you can basically put all the new kinds of interactions on a little plot. You have a new particle, a new field. Tell me two things. Tell me, number one, how massive it is. And mass in physics corresponds to short distances, because a mass is a vibration, and the wavelength being short means the energy is high, which means there's high mass. So there's heavy particles that are corresponding to short ranges and high energies. There are light particles that correspond to long ranges or low energies. That's one thing you have to tell me. And then tell me how that particle interacts with other particles. Is it only a little bit, or is it very strongly? You will not be surprised to learn that the things we can access, the known knowns, the things we've already discovered, are the ones that stretch over large distances and interact strongly. The things we haven't found yet are those that are either too heavy, we haven't had the energy to make them, or too weakly interacting. Those are the known unknowns in David Rumsfeld's famous formulation. The unknown unknowns would just be the idea that quantum field theory is not right, which is, of course, always possible. There's just no evidence for it right now. So two different strategies for looking for new physical phenomena. Go to higher energies, build a giant particle accelerator, smash things together as fast as you can, or look for very, very weak interactions. Look for very subtle, tiny, high-precision effects. And we are doing both. The Tevatron, right next door, here at Fermilab, and the Large Hadron Collider, which is its spiritual successor, were the high-energy route. This was the energy frontier. You just go to as high an energy as you can. You try to make new stuff. Here is Fermilab. The Tevatron was recently decommissioned, like the old battleship that it was. The Large Hadron Collider is outside Geneva at CERN. It's where the Higgs boson was discovered. The ATLAS and CMS experiments are there. You can't actually see the Large Hadron Collider from the ground because it's 300 feet underground. You could be standing on top of it and not know. Fermilab, at least you can see, which I think any honest accelerator should be visible from an airplane. So what happens, what do these things do? They take protons Fermilab took protons and antiprotons. CERN just takes protons and you smash them together and you watch what comes out. And here's what comes out. Well, what comes out is a lot. The problem is a proton is a mess. You smash it together and, lots of things come out. So there's so many things coming out, and they're governed by the rules of quantum mechanics, that at the LHC, when two protons come together and collide and have an event, you throw away the data about 999,999 times out of a million. Usually what happens in an event is just stuff we knew was going to happen. It's that 1 in a million thing that looks interesting and then we keep it. And so a lot of the effort in particle physics is making sure we keep the right data. So, there's an analogy that is often used here, that doing particle physics is like smashing two watches together and trying to figure out how watches work by watching all the pieces fall apart, right? This analogy is terrible for many reasons. The primary one is that what's coming out when you smash particles together is not what was inside the original particles. Remember, what's really going on are vibrating fields, vibrating to beat the band at incredibly high energies, and their mutual vibrations brings new vibrations into existence in other fields. So when the Higgs boson pops out of a proton-proton collision, it's not because there was a Higgs boson hiding in the protons, it's because you made it. It's like you smash two Timex watches together and a Rolex pops out. And you might think this is very difficult to do, making Rolexes that way. There has to be a cheaper way. For the case of precision watches, there is. For the case of particle physics, this is how we need to do it. The puzzle here, the problem, the issue, the fact of life, is that there is no unique signature that says, look, we found the Higgs boson. The Higgs boson never shows up in your detector. It decays. It has a very short lifetime. The lifetime of a Higgs boson is about 1 zeptosecond, which is very short period of time. Far too short to be noticeable in our detectors. So what we do is we ask, well, what does it decay into? And then theorists come back and say, well, a whole mess of stuff. There's a whole pie chart of possibilities for what the Higgs could decay into. And every one of these possibilities can be produced without making a Higgs boson. So sometimes people say that looking for the Higgs is like looking for a needle in a haystack. But again, that's a wildly optimistic analogy. When you find the needle in the haystack, you know. Looking for the Higgs boson of the LHC is like looking for hay in a haystack. It's like saying that you stack every single stalk of hay in your stack and you're looking for a slightly statistically significant excess at a certain length of hay stalk. And this is why we have charming and highly paid particle physicists going through the data, and what they give us is this. These are the plots that were presented back in July at CERN. When I wrote my book, I don't know if I mentioned the book, but when I wrote my book, these were the two plots that my publisher said, I think that's one step too far. We can't include these plots. They look a little science-y. I mean, there's numbers, there's error bars. They might be scary. And I said, in a very short email, I said, we paid $9 billion for these plots. They should go in the book. He said, OK. So what are you looking at? What you're looking at, this is the energy that comes out when two photons are produced. So you make these terribly complicated protons smashing together. Two very high energy photons come out and a bunch of lower energy stuff. Here's the energy in those photons. Here's how many times you get events with that kind of energy. The smooth downward sloping curve is what you would predict if there were no Higgs bosons lurking around. The tiny little bump, that is because that at this energy, you first made a Higgs boson and then the Higgs boson decayed into two photons. So it's not a different type of thing in any fundamental sense. It's just a slightly higher amount of photons are produced with this energy because you created a new way to make them by first making a Higgs boson, then letting that decay. Now, to the skeptical eye, these bumps aren't very big. In fact, if they hadn't drawn the red line there, you might not have noticed that there was a bump there. But number one, trust me, they do the math. This is a 1 in a million chance that you would get a bump that big if it were not real. And number two, there are two plots for two very competitive sets of experimenters, and they find exactly the same bump in exactly the same place. There's no question that there is a new particle here, and that we now know it is something that we were looking for, called the Higgs boson. So that leaves us in a bittersweet reality. The good news is that we understand all of the laws of physics underlying everything that you see around you right now. That is to say, as you go through your life, the things that, unless you're a working particle physicist, as you go through your life just using your eyes, listening with your ears, touching things with your fingers, everything you experience is explained by the physics we now understand, by these atoms and the other elementary particles. And I added to the background here the Higgs boson field. We understand gravity. All the underlying stuff that makes up you, me, the Earth, the sun, the moon, the stars, the podium, your cat. This is all physics we now understand. And I know what you're thinking. You're thinking, well, I'm not going to believe a grandiose claim like that unless you show me the equations. I know that you like to see, well, so here is the equation. This is all of everyday physics summarized in a single equation. And I won't leave this up here for very long because there are experts in the audience looking for typos. But there's good news and bad news. Finding the Higgs boson was the culmination of a 2,500-year quest to understand the fundamental ingredients of the world that we immediately observe. And we've done that. And this is one of the milestone achievements in human intellectual history. And we should be very, very proud and very, very grateful to the people who did all the hard work. The sad news is we know we're not done. We know this is not all of physics. I'm being very, very careful. This is the physics underlying the immediately accessible stuff of the universe. This does not tell us what happened at the Big Bang. This does not tell us why there's more matter than antimatter in the universe. It does not tell us what the dark matter of the universe is. So we need to go beyond it. We're nowhere near finished it. But if this theory right here fits all of the data we have ever collected in every experiment here on Earth, which it does, how do we move beyond it? We know we're not right. There are experiments outside the Earth that cannot be explained by that theory. There is dark matter in the universe. This is not a simulation. This is data. This is data of looking in one direction of the sky, looking for the perturbations in how light travels from distant galaxies to us, caused by concentrations of dark matter in the universe. This is where the dark matter is. We know it. There's the map of it. It's not just a conjecture. We also know that the standard model of particle physics, the stuff we've discovered in our laboratories, cannot explain the dark matter. There's definitely some kind of particle, some kind of field vibrating out there, and we don't yet know what it is. We have ideas. We have ideas like supersymmetry, and this would be a whole other hour-long lecture if I were going into that. Instead, just sort of be impressed at the cuteness of this picture. So supersymmetry says that for every particle we've so far discovered, there's a friend, a partner, such that for every fermion we've discovered, there's a boson, and for every boson that we've discovered, there's a fermion. So if there are quarks and leptons, if there are fermions in the standard model, the rule is you put an S in the front to make the bosonic superpartners, squarks and sleptons. Not pulling your leg here, totally serious. If you have a boson, like gluons or gravitons, you put eno at the end, so there's gluinos, gravitinos, etc. I just found, to my shock, that one of my graduate students is working on the idea that the dark matter is glue-ball-enos. How are you going to get respect from your parents at home when you tell them you're working on glue-ball-eno dark matter? So we're looking. If this theory is right, there is a chance. It's not 100%. It's not 0%. There's a chance that all of these particles are findable. The LHC is not going to find them this year because it's not running. We turned off the LHC. They're upgrading it. They're almost doubling the energy. So the LHC will come back on in a couple of years, in 2015, and we're going to be looking for all of these particles, and if we find them, then the world will change by quite a bit. But we're not stopping at that. So we have here at Fermilab projects to move forward, try to discover some of these new effects. The Tevatron, the energy frontier part of Fermilab's program, has shut down, but there's the intensity frontier. The idea that rather than doing that obvious thing of going to higher energies, we do the subtle and precise thing of going to smaller effects, more delicate work, looking for tiny little things that can still be just as educational in terms of finding new physics. So at the edge of Fermilab, I don't know if you've ever noticed, there's a sign that says, "Welcome to Batavia, City of Energy." And that will be replaced with City of Intensity, which I think totally works branding-wise. So this is a multi-pronged program. I'm not the world's expert. I'm not going to tell you about every prong of it. I picked out my two favorite examples because I think they're kind of cool. They're all kind of cool. These are my two favorites. One of them is called the muon G-2 experiment, again, because particle physicists have some special genius for coming up with names for things. What does that mean, the muon G-2 experiment? Well, the muon is the elementary particle, the heavier partner of the electron. It has a magnetic field. It's like a little spinning top that has an electric charge, so it has a magnetic field. It turns out that if it were just a single classical particle, there's a number called G, which tells you the shape of the magnetic field around the particle. And if it were classical, G would be equal to 2. But it's not. The muon is a vibrating quantum field. So when that muon vibrates, it gently shakes all of the other fields next to it. Now, we are trained from birth to think of particles, not fields. So what we think of are not vibrating fields, but virtual particles. So physicists think about the muon being surrounded by a buzzing cloud of virtual particles, which are not other muons. They're any particles that could couple to photons and muons and so forth. And it's the combination of all this buzzing cloud of virtual vibrating fields that gives rise to the true magnetic field of the muon. And you plug in the equations, you say, what is the shape of that magnetic field? And you find that G does not equal 2. It's close, 2.0023318354. I forget whether this is the theory or the experiment because they both agree to very, very high precision. You see, this is a sort of crazily precise kind of measurement. Now, it turns out they don't exactly agree. There's this tiny little difficulty that doesn't quite match, which is good. We're looking for mismatches. So we want to do better. What we're doing is hoping that one of these virtual particles is one that we haven't yet discovered in the standard model. So in other words, we don't have to make a new particle to discover new particles. If we find that the properties of the muon are not what we expect, that can be a discovery of a new particle. That can be what we call new physics. So how are we going to do this? Well, it turns out there's already a muon G-2 experiment in Long Island, of all places, at the Brookhaven National Lab, which is a perfectly okay national lab in its own right. They have a muon storage ring. What they don't have are nearly as many muons as they can make here at Fermilab. So what you'd like to do is an experiment like this, but do it at Fermilab. The problem is the ring is in Long Island. You have to build a whole new ring, and no one's going to give you the money for that. Particle physicists are nothing if not resourceful, so they're going to put that ring on a boat. They are taking the magnetic part of this ring, they're putting it on a boat, they're going to sail it. This leaves next week. I'm not making this up. They're sailing it around Florida, up the Mississippi River. They're going to unload it at a Costco near Fermilab in the parking lot, and they're going to put it on a truck. This is not an image because they haven't done it yet. This is a Lego model of, and then they're going to drive it down the 88. My suggestion was Friday at 5 p.m. because they can't move very fast. It needs to move at 5 miles an hour. It's already moving at 5 miles an hour. What they're actually going to do is midnight on a Saturday or a Sunday. I don't know. That seems like a missed opportunity for PR to me. So this is one of the things that Fermilab will be doing at the Intensity Frontier. The other thing that is really fun is the neutrino program. So again, a million things going on. I'm not going to explain them all. The thing that is especially cool about this is that neutrinos are very weakly interacting particles. Not so weakly that we haven't found them. We know that they're there. We've discovered them. But you got to work at it to really detect them. And what the particle physicists, again, very resourceful people, have done is turn that difficulty and made it into a virtue. You want to look at the properties of neutrinos after they've had some time to evolve. Because what neutrinos do is they change flavors. There's an electron neutrino, a muon neutrino, a tau neutrino, and they oscillate into each other, back and forth. But it takes some time, and the neutrinos tend to move close to the speed of light. So what you do is you make the neutrinos over here at Fermilab, and you detect them in Minnesota or in the Dakotas somewhere. How do you get the neutrinos from here to there? You shoot them under the Earth. They go through the Earth, which is just awesome, I think. And most of them make it. Almost all of them just go right through the Earth. And then you need to build a gigantic detector to just detect a few of the neutrinos that have made it all the way to Minnesota or to here. So these are ongoing experiments. Some of them are already happening. The NOVA experiment is being built right now. It's supposed to start up later. MINOS is already starting. LBNE is a future project. And we're going to learn about that very, very weakly interacting sector of the universe, just like we learned about the heavy, easy-to-find sector already. But that's not all. It's like, I feel like I'm advertising steak knives or something like that. The reason we're here today, one of the many reasons that there's a workshop going on for the International Linear Collider. And this, many of us think, is the next big step after the Large Hadron Collider that has been going on in CERN. The Linear Collider, the International Linear Collider, is something that is so much in the future. It's not that far, but we don't even know where it will be yet. We haven't exactly decided where to put it. The smart money these days is on Japan, because every other country in the world says, I don't want to pay for that. And the Japanese say, well, we don't want to pay for it, but we might pay a little bit. So Japan is the leading candidate for where to put the Linear Collider. The Linear Collider is the obvious partner to the Large Hadron Collider, for reasons I'll explain in a bit. This is a weirdly misleading picture because of this soccer field here. This is the world's largest soccer field that they put for scale. The Linear Collider will be about 31 kilometers across. So this is like a 5-kilometer soccer field. I don't understand why that helps. So the Linear Collider would stretch about halfway from here to Chicago if you built it starting right here in this room, except that the electrons and positrons, the Linear Collider will not be protons or antiprotons, it will be electrons and positrons, and they will move much faster than the traffic on I-88. So why is it a natural complement to the Large Hadron Collider? Because it does something very different. The Large Hadron Collider takes protons and smacks them into other protons. But we already know that protons are not elementary particles. Protons are collections of quarks. And when you accelerate them to these amazing energies, it's not just the 3 quarks that we think of that are important. It's all of the virtual particles that are inside those protons holding the quarks together. There are other quark-antiquark pairs. There are gluons. There's the original quarks. So it all gets squeezed together because of special relativity, moving at 99.9999999% the speed of light. So what you really have is a thin, complicated pancake hitting another thin, complicated pancake. It's very difficult to know exactly what happened, which is why the whole point of the LHC is to do it 1 billion times. 1 billion is nothing. Do it hundreds of trillions of times, looking for enough statistical information that you can really know that something new has been going on. It is a Dionysian way of doing physics. Just do everything loudly and as noisily as you can. The Apollonian way of doing physics, as cleanly and precisely, is the Linear Collider. You take an electron, a positron, which is the antiparticle of the electron. As far as we know today, these are elementary particles. When 2 of them hit, we know that 2 of them hit. At the LHC, you throw away all but 1 out of 1 million events. At the ILC, you will keep the events. You will know exactly what is going on. You can make very, very high precision measurements. So the LHC finds stuff in a sort of haphazard way. The ILC studies stuff in a very, very precise microscalpel kind of way. Is that interesting and worthwhile? Yes, it is. For example, the Higgs boson. We found it now. There was, this sort of nervousness when we were talking about the ILC 5 years ago. What if we don't find the Higgs boson? Now we know it's there. We know it's perfectly situated to make a gajillion of them at the ILC. And what you're going to be doing is, here's this pie chart of ways that the Higgs boson can decay. We're going to study this to death. So what this means is, here are ways that you can make the Higgs boson at the ILC. You make an electron. That's the electron. It collides with a positron, and it makes other particles, a Z that spits off a Higgs, some W bosons and some neutrinos, or 2 Zs and other electrons. And the point is that We have a theory. I showed you the equation back there. We have a theory that makes absolutely definitive predictions for all of these processes. And if the theory is not complete, which we think it's not, if there's new physics lurking, then that new physics can enter in to all of these processes. So it's not just that we found the Higgs, and in order to go beyond it, we need to find another particle. If the percentages in this pie chart are not exactly right, then we have found another particle. If the predictions of our theory do not match the high precision data that we'll get from the ILC, we know that there will be new physics, and we can study what kind of new physics there is. We may even learn about how the universe will end. And this is my most shameless slide of the evening. People noticed, remember the Higgs boson, the whole thing about what it is good for is that it takes a non-zero value in empty space. Why? Because it actually requires more energy for the Higgs to be at 0 than to be at the value that it has. So if you plot that, if you say how much energy is in the Higgs field versus the value of the Higgs field, there's a little minimum, and we sit there. And the energy is not exactly 0. There's a difference between the energy that we have in empty space and 0, and we call that dark energy. We think that that's probably the best candidate for the dark energy that is making the universe accelerate. But also, now that we know the mass of the Higgs, you can predict the whole shape of this curve, the energy contained versus the value. And you might think that it just goes up and up and up. That would be logical, but that does not seem to be how the data is pointing. You might worry that it goes up and then it goes down forever. That's possible, also not how the data is pointing. The data seems to say that we're just on the boundary of either this is indeed the lowest value of energy, or maybe there's another one out there with an even lower value. So what we're saying here is that it's possible that our space around us, our entire universe, is temporary. That what will happen at some time in the future is that in pockets of space that then grow and take over the whole world, the Higgs boson makes a quantum mechanical jump from there to there. The energy is lower. It wants to be here. So in some little bubble, you get a lower energy collection of Higgs field, and that grows at the speed of light, and we all die instantly. Well, you know, we never said the particle physics was going to be pretty. This is what you have to do. You take what the data say. Right now, we don't know whether that will happen or not. We suspect that if it does happen, we're talking about, again, trillions of times the age of the universe. It's not like a rebalance your stock portfolio kind of consideration, but we might like to know whether this is going to happen or not. In order to do that, we need to measure the properties of the particles that we know and love better, and that's what the ILC will do. Finally, the final thing that the ILC will do for us is, well, there's another dozen things, but the one that I'm highlighting is dark matter. Remember, we know there is dark matter. Is this a warning? Am I being told something? It's the dark matter. It's talking to us. This is not my fault. I did nothing bad. All right. Someone's cell phone? Set your radios, folks. All right. Remember, the single most obvious, blatant, unmistakable piece of evidence empirically that we have that we need physics beyond what we know is dark matter. Again, we have pictures of where the dark matter is. We have many, many, many theories for what the dark matter could be, particle physics models. They tend to be a mess. Here is a theory for particle physics beyond the standard model. You know, I showed you the picture from supersymmetry. There were a bunch of partners, but all these partners have different masses, different spins, different couplings, and so forth. What you want is to go from here to there. You want to start with a theory. You want to measure the parameters. What are the masses? What are the couplings? What are the interactions? Then you can predict how much dark matter there should be. You could ask whether it fits the data. And then you can go to your friends who are looking to find dark matter underground. directly detect it and make a very, very precise prediction for where it should be. So right now, we're trying to find dark matter. This is the dark matter decade, the 2010s. This is the time when we have a chance to really figure out what most of the matter in the universe is. And we're at that tantalizing hint stage, which is kind of annoying. But getting the dark matter detectors better, getting the ILC up and running, continuing on with the LHC, we will pin down this dark matter stuff. The chances are good we will pin down this dark matter stuff. Better than 50%, let me put it that way. All right, you've been very patient. So I know you want to know the answers. Where do we come from? What are we? Where are we going? These are famous questions that were asked by Paul Gauguin, and he drew a painting about Tahiti to illustrate these questions. These are the questions that are making us do particle physics, do science in any way. We have found through scientific investigation that this guy was right, that we were made of particles. We know a little bit better now. We're actually made of fields, but the same basic philosophy applies. We have this remarkable notion that seems to be true, that you and I, all of us, all of our thoughts and hopes and dreams are interacting atoms. Atoms moving around in different patterns governed by the laws of physics, governed by the forces of gravity and electromagnetism and so forth. What separates you and me from other collections of atoms, like rocks or dirt and so forth, is that we have this self-referential capability, that we can hold pictures of the universe in our brain, and that we are driven by curiosity to understand more and more of what that universe is. And that curiosity has taken us absolutely amazing places, and it has a chance to take us a lot farther. It's our duty, we enjoy the science we've already discovered. It's also a little bit of our duty and responsibility to make sure that that science keeps going so the generations after ours know even more than we do. Thank you.